Alright, so hello everyone and welcome again to another science video lesson. And in this video lesson, we will going to talk about a science discipline which I think I like most, that is physics. Alright, so in this video lesson, we will talk about a phenomenon. Alright, we will talk about a phenomenon that creates this modern world that we have right now. All right, so if you have an idea what I'm talking about, so it's okay. But if you don't have, okay, that's the reason why we will discuss this particular topic on the for today's video lesson. All right, so let's not waste time. So let's jump to that topic and let's see what topic it is. All right. Alright, so we have here a physics discipline for this video lesson, and we will talk about electricity and magnetism. So certainly is several hundred years ago, alright, there's one person named Hans Christian Ørsted. Discovered the relationship between magnetism and electricity by putting a current carrying wire near a compass, all right? And suddenly the compass respond to the current carrying wire, and he noticed that, or he concluded that this current carrying wire contains a magnetic field that allows the compass to move on a certain direction. All right. So from that discovery, there's one person who is eager to repeat that particular experiment and try to prove or try to discover something else on this relationship between electricity and magnetism. All right. So let's jump to our topic here. So today we were going to have electromagnetic induction. So basically, we will try to find out what is this process all about. And the key question that we have, as I've said earlier, is what is electromagnetic induction? Then the objectives that we have right here is explain how electromagnetic induction works. All right. So next, how changing magnetic field creates moving charges. So how is this magnetic field enable us to create this current inside the conductor? And finally, let's identify some variables that affect the current produced in an electromagnetic induction. So what are these factors? All right. So let's get this over with. Okay. Alright, so we will focus on one person who is the proponent of this process, and that is Michael Faraday himself. Alright, Michael Faraday didn't have didn't have a good formal education. Instead, he devoted his time reading some paperworks and research in Royal Institute of London. Alright, so what happened there is he developed this curiosity about electricity and magnetism. Okay, and he watched Hans Christian Ørsted's experiment about electricity and magnetism, and because of that experiment, he had an idea about this particular process in the long run. Alright, so what do we mean by electromagnetic process? So this is a process by which we use magnetic field to produce voltage in a complete circuit. So take note, you must have a complete circuit in order to produce a current. So without a complete circuit, all right, so without a closed loop, all right, closed loop of wire conductor, you cannot produce a current. All right, so okay, so that is what electromagnetic induction is all about. What is very important here is the magnetic field. All right? What is very important here is the magnetic field. So without this magnetic field, you cannot produce a current in a complete circuit. All right? So according to Michael Faraday, he discovered that he discovered that with some when you move a conductive substance through a magnetic field, the current will be produced. All right, so he worked the other way around. The magnet moves on the conductive substance, and he got the same result. All right, so In this particular discussion that we will have today, we will try to discover what are these things that he discovered in this electromagnetic induction. Alright, so if you move a magnet near a coil of wire, basically the current will produce, and this is what they call the electromagnetic induction. This is the opposite. All right, this process is the opposite of your electric motor. All right, this process, the electric motor. All right, with the use of magnetic field, it converts electricity to mechanical energy. In this case, that we have right here, we convert mechanical energy to electricity. Alright, so that's the difference. Now, what do you mean by induced? Induced means to produce something from. Alright, to produce something from. Alright, so what is that from? From a moving magnet. Alright, from a moving magnet. What is that something? And that is the current. Alright, when you move that magnet from to a conductor, you produce a current. And before current, you have voltage first, then the current will flow afterwards. Alright, so that is what we meant by electromagnetic induction. And if you move electric charge, alright, and it creates, the moving electric charge creates magnetism, alright, in the previous idea, alright, that the moving charge creates magnetism. If you move the magnetic fields on a conductor, or if you move a magnet through a conductor which contains this magnetic field, it creates an electric charge. Alright, so vice versa. So this is opposite. And electromagnetic induction is the baseline. This is the basic idea of electromagnetic waves. Alright, so the light itself. Alright, because of this interchangeable ideas that we have right here, that moving electric charge creates magnetism. If you inverse that one, moving magnetic fields will create charges. Alright, so this is what electromagnetic induction is all about. Alright, so if the magnet is stationary, alright, if the magnet is stationary, you cannot produce a current on a wire. Alright, you cannot produce a current on a wire. What is very important here is the magnetic field should be changing. How do you change the magnetic field? Alright, how do you change the magnetic field? Now, if you move the magnet in and out of the conductor, that's the way, or that is one way of changing the magnetic field. Alright, so how is that possible? Alright, how is that possible to produce that changing to have a changing magnetic field? Alright, so when the magnet is near the coil, alright, as we all know that the north pole of the magnet contains greater intensity of magnetic field. Alright, so it contains greater flux of magnetic field. Alright, so if you move this north pole near the conductor, alright, the conductor experience an increase in magnetic field. Alright, then when you move out this north pole away from the conductor, the loop of wire experience a less amount of magnetic field. So by moving the magnet near the coil and moving the magnet away from the coil, you change the magnetic field. And it will produce a current. Alright, so you create a changing magnetic field. Alright, and aside from that notion, alright, aside from moving it, okay, you can change the polarity of the magnet. So as you can change the magnetic field as well. As we all know that the south pole, if we will going to draw the magnetic field of this magnet, the north pole is moving away from the magnet. Alright, so the magnetic field of the north pole is moving away from the north pole itself, and on the south pole it goes to the south. Alright, so the magnetic field is going towards the south. So there is a difference between the direction of the magnetic field that you have right here. Then when you flip them, alright, when you flip these poles together, you change the magnetic field as well. Alright, so those are the two ways that you can change the magnetic field, alright, in your electromagnetic induction. Alright, so the thing here is, please take note of this idea. If the magnet is stationary, you cannot produce a current. Alright, so let's take a look at this simulation. Alright, so in this simulation that we have, okay, so as you can see, let's click the pickup coil. Right, let's place it on the middle. Okay. Now, as you can see, if the magnet is not moving, all right, if the magnet is not moving, you can, as you can see, the electrons inside your conductor is not moving as well. All right. Therefore, there is no changing magnetic field. But if you move this one, there will be a changing magnetic field. The coil of wire, all right, when I put this north pole near the coil of wire, it experiences greater magnetic field, and when I move it away, it experiences less magnetic field. And doing it repeatedly, all right, the coil of wire will experience this changing magnetic field. So as with change of polarity, for example, if I flip the polarity here, all right, so I change the magnetic field, all right, I change the magnetic field's direction, all right, as I change this polarity. And what happened to the electrons, or what happens to the electrons inside the loop of wire? It moves, all right, it moves, and it generates electricity, as you can see. All right, so moving the magnet or flipping the polarity are the two ways of changing your magnetic field. All right, let's go back. Okay, so now in this case, all right, in this case, okay, how do we produce this okay, how do we produce this current? Now, if the magnetic field, the key idea here is, if the magnetic field is increasing, the induced current, all right, is in one direction. All right, so later we will go to the simulation to visualize this one. And if the field is decreasing, the induced current will be in the opposite direction. All right, so what do you mean by this one? Okay, so let's take a look. Okay, now if you put the magnet facing the north on the loop of wire, the direction of the current is going to the negative side. Now, when you move out the magnet, all right, when you move out the magnet out of the coil of wire, the direction of the current is towards the positive. So, meaning to say, it is not in a single direction. It is in a two-directional motion. Yung the current that we have right here has a two-directional motion. It depends upon the direction of the moving magnet. All right. So if we take a look at this, all right, if we take a look at this simulation that we have right here, right? So let's have a instead of north, let's have the south going inside your loop of wire. Okay, so as you can see, the electrons is moving upward. All right, when I pull out the south pole of this magnet away, all right, so the electrons inside this loop of wire is going downward. Okay, so upward, downward, upward, downward. All right, so it doesn't stay in one direction. All right, so later I will reveal what type of current is that. So okay, let's finish this one out. Okay, so take note that one. Alright, so take note that one, that if you move, okay, let's change the polarity. So in North Pole, alright, the magnet is going, the electrons inside the wire is going downward, and when you pull it out, it's going upward. So it changes the direction of the current depending on how you change this magnetic field in general. Alright, so okay, let's go back. Okay. Alright, so in summary, it looks like this. Alright, so it looks like this. The permanent magnets that you have right here, so the permanent magnets that you have right here is spinning. Alright, so it is spinning. So as it spins, it changes its polarity. Alright, in every part of this rotor that you have right here. Now, as you do, Alright, as this coil of wire encounters different polarity that you have right here, it creates this electric current. Alright, so as you can see here, when the north pole is faced with this loop of wire, the direction of the current is going to that direction stated on this diagram. Alright, when it is when the south is facing the loop of wire, the direction that we had earlier, this one, it is already changed, and that is because the south pole of the magnet is facing this loop of wire that we have right here. So meaning to say, that these two poles of your magnet, the north and south respectively, creates a current with two different direction in a loop of wire. Alright, so that is one thing that is produced in an electromagnetic induction. Alright, so now I forgot to mention that the electricity that you produce here, alright, as you can see, it is alternating in direction. So we will use that same word. The electricity that is produced here is an AC type of current. Alright, so or alternating current. Right, so as you can see on this diagram, that the current is changing its direction as two different polarity of the magnet encounters or interacts with your loop of wire that you have right here. Alright, so that is alternating current. Okay, so what is this idea? What is another idea about this law of induction that we have right here, or this electromagnetic induction? Now, according to Michael Faraday, that a moving magnet induces current in a coil of wire only if the magnetic field of the magnet passes through the coil. So that is what he observed, alright, in this particular process, and very simple idea. Right? By moving the magnet into the coil of wire, you create electricity. That's it. Right? Very simple and world-changing idea that you have right here. This is the main statement of Faraday law of electromagnetic induction. All right. So take note, or just remember this particular statement that you have right here. Okay. So and also take note that only a moving magnet can create or only a moving magnetic field can create an electricity in a current carrying conductor. Alright, so this was Michael Faraday when he was at his young age. Alright, and he found out as well, alright, based on his experiment, he found out that the induced voltage that the induced voltage that is produced on the current carrying wire is proportional, alright? So that is proportional to the rate of change. Now, what is this rate of change? Alright? This rate of change that he is talking about, this is the speed. Alright? This is the velocity of the magnet. Alright? So if you look at the velocity formula, so velocity is equal to distance over time. So whenever you hear the word rate, there is always time on it. Alright? There's always time on it. So meaning to say that the velocity of the magnet is somehow directly proportional to the induced voltage, alright, that is produced on the current carrying wire. This is the heart and soul of your electromagnetic induction. Alright? This moving magnet thing that we have right here. And if the magnet is moving 2 meters per second, alright, if you take a look at this voltmeter that you have right here, so generally it is 32 volts. But if you increase the rate, alright, if you increase the rate of movement of your magnet, alright, to 4 meters per second, it becomes 0.64. So meaning to say that the movement of the magnet is directly proportional to the voltage that the current carrying wire will produce. Alright, so if the voltage is greater, so as will the current. Alright, so as the current. So it depends on the resistance of the wire. So assuming that the resistance of the wire is 0, so those two together will produce they are directly proportional. But in reality, all wires have its certain resistance, so maybe the current will be more or less, all right, depends on the resistance of your current carrying conductor. Alright, so the Faraday's law says that the current in a coil is proportional to the rate of the at which the magnetic field changes. Alright, so in order to demonstrate this one, so maybe you are not satisfied with this. Alright, so in order to demonstrate this, okay, so as you can see, if I move this magnet slowly, look at the right. So look at the light that is produced above. All right, it is less. All right. So if I move it slowly in and out, it is less. But if I move this one, all right. So if I move this one at a greater rate of velocity, as you can see, it produces greater amount of current. Right, current and voltage. All right. So as you can see here, all right. So as you can see here, moving the magnet regardless of what pole it is. Okay, so moving the magnet faster creates greater amount of electricity. Alright, so there you go. Okay, so with that, okay, so with that, in order to sum up this Faraday law in electromagnetic induction, what you have right here is a formula of those factors that we have, okay, on this particular process. Alright, so let me have this statement. Okay, he learned that if you change the part of the flux, so what do you mean by flux? This is a fluid. Alright, he considered the magnetic field as a fluid. Alright, so over time, you could induce a current in a conductor and thus creating a source of EMF. EMF is also known as voltage. Do not be confused on that. They are the same thing, all right, with different names. All right, so potential difference. So no matter how you called it, it's the same thing. It's voltage. And since we are dealing with time, so where do we get the time there? All right, it is on the velocity. On the velocity of what? Velocity of your magnet. All right, so if we put that velocity, all right, in the movement of your magnet, we can call it the rate of change in magnetic flux. Alright? Rate of change in magnetic flux. So what do you mean by this one? This is the amount of magnetic flux, or this is the amount of magnetic field that passes through a certain area. This is the total. Alright? Alright? Magnetic flux is the total magnetic field that passes through a certain area. And in our formula, there is an area. Alright? So there is an area. So what do we have right here? What do we have right here? So the greater the area, all right. So the greater the area that we have, okay, it creates a lot of voltage, or it creates greater amount of voltage. So the voltage is somehow greater. All right. But if the area is small, all right, if the area of the what are we talking about here? What is this area all about? This is the area of the conducting wire. Alright? This is the area of the loop. Okay? So the area of the loop. So if the area is less, so as the voltage that will be produced is also less. Alright? So that's how the area is all about. So it is a directly proportional thing. Alright? So what do we have here on this formula? Okay? These are all the factors, all right, that affects the amount of voltage that is produced. Okay, so number one is the number of turns of wire. All right, we have the N over here. This is the number of turns of your wire, or the loop. All right. Next one, we have the magnetic flux over here. If we disintegrate them, if we disintegrate this symbol, it is obtained using this formula. Magnetic field intensity, alright, this is the strength of the magnet, times the area, then the cosine. So meaning to say, there are two different things. At cosine 0, that will be the perpendicular, alright, in this pattern. So at cosine 0, that is the maximum Alright, so that is the maximum magnetic field or the maximum angle that you can produce a maximum voltage. Alright, at cosine 0. But if you have a cosine 90, alright, if the coil of wire is at 90 degrees, alright, 90 degrees in respect to the magnetic field, it will produce no voltage at all because that is 0. Alright, cosine of 90 is somehow 0. Alright, so that is the parallel or the perpendicularity. Alright, so perpendicularity and divided by the time. Alright, so as the change in time is alright, if the change in time is very small, alright, you can produce a lot of greater amount of voltage. But if the change in time is very high, right, if the change in time is greater, that is the voltage will be produced is very low as well. All right, let's take a look at it in the simulation. All right, let's go back to this simulation. So thank you for PHET for providing us this one. So without this simulation, I don't have any idea how we'll be going to visualize this thing that we have right here. All right, so okay, let's start first with the magnetic strength. All right, so if you decrease the magnetic strength down to 10%, so as you can see, no matter how much you move it, it will produce small amount of current. Right, but if you increase the magnetic strength to 100%, so by moving it, even though it is slow, alright, so as you can see, it produces greater amount of current. So magnetic strength, alright, so magnetic strength and the amount of voltage is directly proportional to each other. Alright, so they are directly proportional to each other. Alright, next one. On the formula, we have area. Alright, so let's decrease the area of the loop. Alright, let's see at constant strength that you have right here. Alright, so as you can see, alright, so if I move it slowly, the current that is produced is very small. Alright, but if I increase the area 100%, right? So as you can see, it creates a lot of current. Because what is the reason behind this one? Because in a small area, as you can see, there are small amount of magnetic field. There are small amount of flux that enters to that small area. Alright, there's small amount of flux, so it is limited. So there are a lot of flux here outside. There are a lot of flux outside that particular loop of wire that is not entering that particular loop. Okay, so it remains outside. Only those which is part of the area or included in that particular area will be the one who will enter. So as you can see here, we have just 1, 2, 3, right? So only 3 magnetic field can pass through that particular area. So hypothetically, all right. But if we increase the area to 100%, as you can see, there are a lot of magnetic field that the area can accommodate. So therefore, more magnetic field in a greater area means more electricity that will be produced. So that is why if you will create a generator, make sure that the area of this conducting loop is greater. Alright, so as you can see here, alright, so there are a lot of magnetic field that can be accommodated on that area. Alright, so that's one. Okay, so we have the area. How about the number of loops? Alright, so let's put this one. Let's make the area constant and make the number of loops to 3. Alright, so you can see, the more number of loops, the greater the electricity that will be produced. Alright, so if we make the loop just one, so as you can see, the electricity that is produced or the current that is produced is somehow minimal. Alright, so that is the loop. So it is directly proportional. Alright, so directly proportional. Alright, so okay, so in this simulation, let's summarize it again. Okay, so that the strength of the magnet is directly proportional to the current produced. Alright? Next one, the area is inversely proportional. Alright? The area is inversely proportional to the current produced. Alright? So, rather directly proportional. Sorry for that. Okay? So the area is directly proportional. So the greater the area, the greater the voltage that will be produced. Alright? Next one is the perpendicularity. Alright, so later we will talk about that perpendicularity. Let's have the number of loops. As the number of loops increases, the voltage or the current that will be produced is also greater. Alright? Now, what is inversely proportional here is the time. Alright? If the time, if the change in time is, the change in time is greater, therefore, the voltage that is produced is lesser. So what do you mean by less change in time? It tells us that the object is moving slower. Alright? The object is moving slower. Right. If the change in time is faster, like the one that I have right here, if I move this object faster, the change in time will be lesser. So the voltage that will be produced is greater. Alright, so those are the factors that affects the production of this current in your current carrying wire using electromagnetic induction. Alright, let's go back to Alright, so basically that is how this formula works. Alright, so let's take a look at the perpendicularity. So the maximum value or the maximum, or if the magnet is perpendicular to the, or if the magnetic field is perpendicular to the coil of wire, alright, so that will produce the maximum amount of voltage. If it is not perpendicular, the one that you have right here, right? If it is not perpendicular, you will not produce any any electricity at all. Alright, so let's take a look at this one. How does the area, alright, so how does the area and other factors affect your electricity production? Alright, so as you can see here, the flux is at maximum. Alright, because at a larger area that you have right here, it accommodates a lot of magnetic field. So that is why it is maximum. Then as the coil of wire is moving on that magnetic field, alright, the area is starting to decrease. That's the reason why the flux on that particular area is starting to decrease downward. Alright, it's going down. Alright, but once you decrease the amount of magnetic field that the current carrying wire encounter, that's the time that you will produce current. Remember, changing magnetic field will produce a current. Alright? So the magnetic field is starting to change. Therefore, the current is starting to be produced. Alright. So next one. Let's go back to the flux above. Alright. If the magnet, or if the loop of wire is parallel to your magnetic field, if it is cosine 90, right? If it is cosine 90 or parallel, just to make it simple, if the coil of wire is parallel to your magnetic field, so the flux starts to become zero. Alright, it goes back to zero. So what happens here? What happens is so that is the maximum current that you will produce. Alright, so that's the maximum current over here that you will produce. Okay, and then as it goes back again, so the magnetic field is starting to change one more time as it turns, as the loop of wire turns the other way around. So what happens to the current? It's starting to go to the other direction. This is positive and this is somehow negative. Alright, so and the flux is starting to increase, alright, one more time down to the negative section of this graph over here. Alright, so again, the maximum flux is achieved, alright, at its perpendicular. Right, at its perpendicular. Okay, so the loop of wire is at its perpendicular, so the current will go back again to its baseline. Then as it moves again one more time to the other direction, right, so it goes back to the positive side of the diagram. Alright? So that is how the area of the loop affects the number of magnetic field that is interacting with the loop of wire. Alright? Okay, thus affecting also affecting also the current produced in the process. Alright, so that is how the Faraday law of electromagnetic induction works in this diagram. Alright, so let's go to the last part of our video lesson that I have right here. Alright, so what are the useful application of this Faraday law in electromagnetic induction? So I think if we don't have this electromagnetic induction discovered by Michael Faraday, basically we don't have a modern world that we have right now. Alright, why? Because all our stuffs that we use, the computer, the laptop, okay, so the electricity that we use, alright, it follows or it uses this electricity that is produced in a process called electromagnetic induction. Now, these are some examples of application that you use every day, this particular process. Number one is the charger of your phone. The charger of your phone contains transformer. Alright? It contains transformer that changes the voltage, alright? Alright, that enters to your phone. Alright, so that your phone will not be burned, alright, will not explode due to differences in voltage. Alright, so another one here, we have a forever flashlight in which in order to charge the battery, you just shake this flashlight and it acts. Okay, the coil of wire here acts as a generator. Once you move that coil of wire, it generates an electricity that charges your battery on this flashlight. Alright, so the transformer that we have right here, without this transformer, alright, the electricity that your home use every day is around 144,000 volts. Alright, so that's that amount of voltage will not be allowed to enter to your appliances, or else your appliances will explode. So thanks to this transformer that uses electromagnetic induction, it changes this voltage from higher voltage to a low voltage form. Alright, next one, we have the generator. So without this generator, probably we don't have any electricity at all. This is the heart and soul of electricity production. Alright? Some generators are attached with turbines that is attached to the waterfalls. Alright? So the hydroelectric power plant uses that. And with the kinetic energy that comes from your waterfalls, it is converted into mechanical energy, then electrical energy, and it is delivered to your home. Alright? So generator. Okay, so they are very, very important device under electromagnetic induction that uses this electromagnetic induction. Alright, so we have right here a microphone. Alright, a microphone is an electromagnetic induction application. Alright, so metal detectors. Alright, so if you are wondering what makes microphone an electromagnetic induction. Alright, so if you speak on the microphone, the voice generates this mechanical wave, and these mechanical waves push this coil of wire over here, this one, push this coil of wire up and down. Alright, it pushes it up and down on the magnet at the middle. So as you remember, changing magnetic field, alright, moving magnet or moving coil on a magnetic field creates electricity. So once this coil starts to move up and down, it creates an electricity that goes out to your amplifier or speaker. So that is why you can hear my voice right now because of this microphone that I have right here. Alright, so okay, so a simple thing that we have right here uses this electromagnetic induction. Alright, so that's how. Another one, metal detector. If you happen to see some security guards on malls and in airport, you have your metal detectors over here. Alright, so metal detectors also uses electromagnetic induction. Alright, so right. So basically, that is that is how our lesson is all about. Okay, it's all about electromagnetic induction. So I hope you did learn something from the video lesson that we had earlier about electromagnetic induction. So this is a very important process, all right? So imagine a world without electromagnetic induction. So probably we are still using candles or burners, something like that, okay, in order to light up our surrounding. Okay, so with that, if you gain some knowledge on this video, you can hit the thumbs up on this video. All right, like this video, so it means a lot to me. All right, and if you want to be updated with more videos like this in the future, hit subscribe and also its notification bell. Now, if you have a question, just write it down in the comment section, or suggestion that you want me to create another video in the future, right? Or any topic that you want me to create in the future, all right? Just write it down in the comment section. All right, so I believe that's it for this video, and let's see each other on the next video. All right, so peace out, everyone.